My name is Malcolm Doney, and it is also my pleasure to introduce you all to Professor David Berman, who is the Professor in Theoretical Physics at Queen Mary University in London. And his main research interests are in M theory, which is described as the non-perturbative vision of string theory. And you can ask him about that, and we may explain it to us later on. But recently he's been interested in backgrounds to string theory and in things that are intrinsically stringy in origin, not just solutions to supergravity, and these go by the name of T-folds. We're also very pleased to have with us today Grenville Davey, a Turner Prize-winning sculptor who collaborated with David in that fascinating piece of sculpture which is on the plinth over there. So do go and have a look at that. It relates to all the things that we're talking about today. Now, I'm going to get off now because David says that if you have any questions, he's very happy for you to ask them as he's talking. So if you want to know, for instance, how long a piece of string is, then you can ask him when it occurs to you. You don't have to wait to the end in order to save it up. All right? So that's a warm welcome for David.
Thank you. Okay, so what I'm going to do is talk about time. And the first thing to realise is that there's really three aspects to time that concern us. And they're very different. So we've got to first of all disentangle what these three different aspects of time are. The most simple one, which is really what first concerns scientists, is that there is time that can be measured. There is the notion of duration that you measure with your clock. And in that sense, time is just like a distance in another dimension, but instead of using a ruler, you use a clock. That's a very simple idea, and it's a very quantitative idea in the sense that we can attach numbers to it, we can measure duration, and that we can talk about physical laws involving duration of things that we measure. But that's not very human. The reason why I think time has interested artists, and this has been a subject of this exhibition, is that there is a human experience of time, and we experience time moment from moment, and crucially, there is a direction to time, that there is what's called time's arrow. This is very distinct to when I spoke about the distance in space. When I talk about the distance from me to you, then really there's not an arrow to it unless I say, okay, I'm going to go towards you or something. You can think at a distance doesn't necessarily have a direction. And yet we all feel deep down in ourselves, in the way that we experience life, there is a direction to it in the way we experience time. This is not something that we actually measure with our clocks. With our clocks, we only measure the overall distance in time, not the experiential arrow that we all feel. So what I'm going to try and do, so I should add, I said there were three aspects. Yeah. The third is exactly this notion, which I've brought in with the arrow, which is how we as human beings experience time itself. So that can be very different to how time appears in nature and how scientists measure time. And even with the arrow of time and its directness in the physical world, that can still be different from our experiential, existential notion of time. So I'm hopefully going to try and get to where some of the physical notions of the arrow of time can be related to our experience of it. But there's always a danger here. Just because I can provide you with an arrow based in physics, you've got to decide yourself whether it's satisfactory explanation of how you as a human experience time. Okay, so we're going to do it one step at a time. So, I really have to explain what Einstein did in special relativity. Okay? it's very misunderstood. And part of the problem is the name. Okay? So relativity has got this idea of everything being relative. Okay? And so what was relativity about? It was about, you've got the laws of physics. The laws of physics stuff happens. It can happen here and at this time, and it can be related causally or not to an event over there at another time. And Einstein asked the question, when you describe here and when you describe now, you do so with respect to an origin, yourself. So when I say Grenville is 3 meters over there, well, that's with respect to me. And when I say this event is happening at 35 minutes past 2, that's with respect to the watch that I hold. Now, each one of you in the room has also got their notion of distance to me, let's say, and the time. And we're all probably agreeing on the time, plus or minus our watches being a bit off. But our distance is an interesting one, because you're all placed in different places. So when you describe where I am, the people on this side of the room will go, well, he's a bit to my left. The people on this side of the room will go, well, he's in front of me to the right. So obviously the notion of left and right, of where an event is or where someone is, depends on where you are. This is not a big deal. It's obvious. So what we tend to talk about is not how much forward someone is and left or right, but the overall distance. And what do we mean by the overall distance? It means that we combine different directions and distances together into one number, and that number won't actually depend on the different ways in which we face. So for example, if I look at the distance from me to the camera, when I'm facing it, then I can say it is whatever it is, 3 meters that way. But if I rotate this way, now it's 3 meters to the left, not in front of me. But we all know the distance between me and the camera has not changed. It stays the same no matter which way I face. Are we all happy with that idea? It's irrefutable. So it's all very well to have a notion of where things are in terms of to the right, to the left, in front, behind, but the thing that doesn't change and doesn't depend on which way you're facing is the overall distance. Now, what Einstein did is say, that's great. We've all understood that's basic geometry. The Greeks came up with that. But now we've got this notion of time. We think of things as events that happen in our lives or in the universe, and we've got to give 4 coordinates. 3 for space. So when you were told to come here today, you were given the fact that it's in this gallery, and which is wherever it is, north, south, east, west, and then how far up. It's effectively 3 coordinates in space, and 1 in time. So you were given 4 coordinates. Okay? You were told it was going to end at a certain time, or at least I hope you were. So then, you can ask the question, is there an overall distance in space and time of the length of this thing? Because I've got 4 coordinates in space, sorry, 3 coordinates in space and 1 of time, and then we want to know, how do we combine? If there is such a thing of space and time together, how do we combine them to give an overall distance in space-time, just as I give an overall distance in space from me to you? Okay? And Einstein described how to do that, how to provide a way of combining space and time into one thing to give an overall distance. Now, that sounds like a little piece of mathematical trickery. Yes, you can then link it to 4-dimensional geometry, and that might be sort of interesting, because then it says that the events of your life unfold in a 4-dimensional space. As you exist, you trace a line in this 4-dimensional space-time, with each point in the line being your personal time. So it's fun, but does it buy you anything? Does it get you anything new which people could experimentally measure? And this was the surprising thing. It does. Because it says, just as when I was describing the distance between me and the camera, I could rotate, And it was no longer about what was in front of me or to the left of me that mattered. That was just a choice. Okay. So then Einstein asked the question, what's the equivalent of rotating in space and time? There's something that's going to be left the same, which is the overall distance. And then what he realized was, just as I can change the amount that's in front of me compared to the amount that's left of me, you could change the amount that was in time and the amount was in space. You could rotate space and time into each other. And the way that you would do that would be by moving at different speeds. There is no intuitive way you can sit here now and understand what I've just said. None. And so this is why it's very hard to explain these things and why Einstein is a renowned genius. Okay? So then I have to say, well, how can I explain that to you? So Einstein worked out, with mathematics, given his combination of how time and space could rotate into each other, you're used to the fact that this can rotate into that as I just move around. So then he said, well, if you move at a different speed, can that then change what is space and time and move them into each other? The result being that if, for example, I take something and make it less time and more space, a clock will run more slowly and a ruler will extend, leaving the overall combination the same as before. And then he predicted how much will time slow down as you go faster. And he showed, in a very concrete way, that it will slow down ad infinitum until it will stop as you approach the speed of light. That was a prediction of Einstein. So then people measured it. They went and they looked at clocks on quickly moving bodies. Started out, they put atomic clocks on rockets. What do you find? The clock slows down compared to the one that's not moving. Because, from its perspective, its time moves more slowly. It's facing a different way in space and time as combined in one thing. I am aware this is hard to grasp. The reason for that, and this is where I'm always stumped, is that the language of nature is mathematics. I've tried to describe 4 dimensions and the idea of some distance in 4 dimensions being the same, but how could you change the components of that distance? We can't see it. We can never see or understand 4 dimensions, but we can use maths to write them down. But then we can make predictions and measure them. So what Einstein did, yeah?
Is the joy then in being able to measure things?
Yeah, joy.
No, I just think...
No, it's a good question. I have never found joy in measuring things. It's miserable business. But...
change joy to point to... was Einstein's real joy and point that he wanted to be able to measure the unmeasurable?
I think what... You see, there's a great danger in when you've got a mathematical language that you can get carried away with it. You can look and think of all the mysterious stuff that you can do with maths that people don't understand and come up with all sorts of results. And then, so that, the whole of mathematics is full of that, and that's great fun for a lot of mathematicians. The miracle, though, happens is if you do that game and nature happens to agree with you. So I'm not going to say it's the point that Einstein never measured anything, but I think there was an enormous shock to the world that something that seemed like one of these thought games, a piece of philosophy of how we combine space and time and play some game of mathematical geometry, would then lead to a prediction of how clocks move more slowly, and it's exactly measured, that's how slowly they moved. If it had not happened, then you go, that's an interesting piece of maths, nothing to do with us. But it's always a good question of what we want. Do we want just ideas, or do we want ideas that reflect nature? Sometimes ideas might be enough. Yeah?
I like the idea of the sat-nav that says you're going to arrive in an hour. Then you get stuck in traffic, and 20 minutes later it says you're going to arrive in an hour. So
She's interested in that. I'll go to the next bit. So this was special relativity. So this was the idea that time and space, you've got to join them together. You've got to make it into one thing. It's not what we experience. We always experience as time being very separate to space in this way. And it's for a simple reason. I said to rotate in time and space, I needed to move at a different speed. But the problem is I've got to move it near the speed of light to get that effect. I've got to have rockets going off to get these small effects of time. So it's because none of us has moved at near the speed of light, we don't experience it. If we're a bunch of beings that could travel really fast, then our whole intuition about how time would work would be completely different. We would have this built into our brains because automatically we would experience it every day, every time we moved. Just in the same way that, I think I can do this. I have a geometric notion. People who are artists in this room are used to the idea of seeing space and rotating things in their head. You don't do that with time because you've never experienced it, just because you move too slowly. Now, someone said GPS. So Einstein's next trick, was after deciding to combine space and time together, he then said, should that combination always be the same? So he then said, what if it's not? What if sometimes we add space and time together in different ways? So this then leads to the idea of that we add space and time together, and actually you can have it depend where you are. So that time can be different at different points, and space different at different points. So it's like taking, this is what they always use, a rubber sheet, and you put on your rubber sheet a ruler and you mark out a grid. So now you've got a ruler on, a grid on the thing, you've got this notion of distance. And now you take that rubber sheet and you stretch it. And then you can see that the marks can change of how far the rules are depending on how it's stretched. And you can do crazy stretchings. You could put weights here and weights there and make the whole thing bend in all sorts of weird ways so that the spatial bits are all different, in all different locations on there. So now we get another reason why Einstein's a genius, is that corresponds to space-time. It can bend and stretch, that the distances that we measure, if we have rulers and clocks at every point in space-time, they have the freedom to run differently and measure differently depending on where they are. And so this is another experiment. So I think Andrew Marr mentioned it last night. This was first, I think, proven over the height of about 60 feet only, where a clock at the bottom went more slowly than a clock at the top of a tower. That's just basically saying that the notion, that grid that measures a distance, changes depending upon where you are. And here's the cute one. GPS, which relies on satellites in orbits with atomic clocks. If you know how GPS works, every time you look at your phone and it gives you a location, it's actually tuning in to 3 atomic clocks that are in orbit, sometimes a few more. And then it gets the time from each one. The clocks were synchronized when they first were sent up. And then it gets a difference in time from each clock, which then tells you how far away the satellites are, and then they can triangulate where you are. Okay. The curious thing was, when they were working this out, they then went, you know what, there's an issue here. Because they're up in a different place, relativity will mean the clocks will actually move more slowly and be different. And the story goes that GPS was first developed as part of missile guidance for the US military, and the general involved didn't believe it. So he insisted that there would be a switch on GPS, which is whether you believe Einstein or not, in the software. Yeah, Einstein was right. And the curious thing was, it's something like your GPS will be wrong by 30 meters a day from when the rocket was launched if you don't take relativity into account. And that's just a practical thing, but it shows you it's a small effect, but it's an effect that each one of us use all the time, that time up above is different from time below. Yeah?
Yes, just really interesting talking about mathematics as the language of nature and how we have all these results that show that there's something fundamental to the way these equations work. And I was just wondering, do you think of mathematics as like a language like English, which is like a set of symbols that refer to things out there that we're just referring to? Or does it have some kind of extra reality to it that has a structure?
Brilliant, okay. I would say it's not like English in the following way. What maths really is an axiomatic system of logic. Within English, just because something is grammatically correct doesn't make it true. The whole point of maths is that you construct the grammar so tightly, you consider everything that is true that is grammatically correct. That's the first step. Then you say, do I consider it as being related to the world or something else? So this is where I come out as a Platonist and then say, shocking, which is, I believe that all mathematical truths refer to something, but it may not refer to the physical world. But I believe that as mathematicians we discover mathematical truths, but you know, this is philosophy. There's a question back there.
I was just wondering, do you feel that mathematics is complete and consistent, or was there a little wobble about that once?
Right. Well, we know mathematics cannot be complete and consistent due to Gödel's theorem. So for those of you who don't know, we've got off the point, but why not? Actually, it relates to relativity. Gödel said that you could never have a system of mathematics which was powerful enough to encompass the natural numbers, and it's arithmetic, which you'd want most maths to do, and it contain all mathematical truths and not be inconsistent. So in other words, you've got a choice between consistency and completeness of all truths. Mathematicians have gone for consistency, which means there is always something that is true in mathematics you can't prove. You've got to decide if that worries you or not. It's interesting you mentioned Gödel. Gödel was a great friend of Einstein in Princeton, and actually one of his contributions to relativity, very much in the nature of how Gödel proved his theorem about inconsistency, is that Gödel came up with a space-time closed time-like curves. That there would be a space and a space-time that would bend and stretch and have these things. And it's not just that you take a rubber sheet and you bend and stretch it and all these marks go. You take the rubber sheet and you pull it over into a loop. So you can go round and come back on yourself and then come back to where you started from in time. And Gödel came up with that as a solution to Einstein's equations.
Is that the Mobius?
No, that's just called Gödel space-time. Mobius thing's a bit different. But the curious thing about that is physicists and mathematicians have not managed to refute that Gödel space-time. It still seems like a possible physical thing that could happen to space and time, that we would then, in some sort of Nietzschean eternal recurrence, emerge back to where we started from, and that what you guys have got to realise, you might end up here again. But it's something which I think physicists are worried about.
What, ending up here again?
Not that specific problem, but about ending up in a closed time-like curve where all of the universe then re-emerges back at the same state in the future, coming back in time. And that's something which doesn't seem like you want it to happen, but it's very hard to find maths which says that it shouldn't. That's what I mean.
Or couldn't.
Or couldn't, yeah. But at the moment, well, this is what I'm saying. I can't say couldn't because we don't have a proof that it can't happen. So it seems like it shouldn't. Meaning, doesn't seem very intuitive. Okay. Time seems like you'd want it to not go back on itself. But there are solutions which allow it in relativity.
But is there a computation of the likelihood?
Oh, good question. No, I'm going to say no. But it's a very good question, actually. Now, so this has been about, thus far, this notion of distance in time and space, and what Einstein did in terms of bending it and stretching it, and how to combine it together with space, and you get this, this picture, this rubber sheet bending and stretching what space and time is. I've emphasised it's so distant from how you are experiencing time right now. I've said the reason why you don't see it is you don't move fast enough, because you don't go through, can't rotate yourself in space-time, and to be honest, you don't experience that change in time because you don't live near very strongly gravitating objects like black holes and so on. So, although we can now measure these things, and we can now measure black holes colliding, we can see direct photographs of black holes, it's not something you experience. So how can we then get back to what is the thing that's relevant to how we experience time? And this is the notion, and now this goes way back to the 19th century and the laws of thermodynamics. Okay. So, a philosopher once said that every generation in science uses the technology of the time to explain the universe. Famously, the leading technology of the time, things like clocks. So people describe the Newtonian clockwork universe. When we ended up in the Victorian Revolution, in the Industrial Revolution, we had this whole world of machines, of industry, of engines, and so on. And people started to think of the universe as a heat engine. Maybe so, why would you ever do that? So, and this is where people started to think about the laws of thermodynamics. So what are thermodynamics? It really is the laws that govern heat, disorder, useful energy. Please note the word useful, not necessarily just energy, because not all energy is useful. Okay, from which you can extract work to do stuff. When people were doing this, they introduced the idea of something called entropy. Okay. So entropy is the measure of disorder. So a good example is the air in this room. The air in this room is incredibly disordered. It's all bouncing around, spread evenly throughout the whole thing, completely random. We've all got an equal amount of it, roughly, thank God. It's not in any particular special state. If you think of all of the locations of molecules where they could be, and then just let that be, each molecule choose at random where it wants to be, you'll end up with how the air is in the room. And you could roll the dice again, and the 10 to the 32 air molecules each pick where they want to be in the room, you'll again end up with it all equally distributed, all at the same temperature and all at the same pressure. The converse of that is that you would take all of the air in this room and shove it in that corner up there in about a 1 centimetre cube square. That would be very ordered. That would require huge amounts of work and energy expended to then take and order and put together all the things in all the air molecules in this room. When I go into my children's bedroom, it's a very similar process. It's scattered randomly, everything is there, and then you put in work and energy, and then you order it. But then what happens is time. Because one thing is for sure, over time, when my children are in their room, the disorder increases. And it does so actually for very genuine physical principles. They will do random events of this, that, and the other, and unless they consciously decide, I will make it more ordered, any process will make it more disordered. Okay? Just like as we move the air about in this room, any random moving about the air in the room, if I do this, doesn't really affect the entropy in the room. I've got to work really hard and generate some sort of vacuum engine to work very hard to put it in that corner. Okay. So this is the notion of entropy. It is disorder. Okay. And then we've already said something, which is that disorder increases with any process, unless you have the free energy, the energy to consciously create the order. Okay? Are we happy with this idea? This one's easy. Go on.
Is it time that does the differing?
Well, so this is
Is it the entities within the time?
Yeah,
that are
that's right.
The
Good.
children in the bedroom?
Good. So this is where I'm trying to link it to time. It's the process, so the children in the bedroom, the me moving about, or whatever it is. Now, I've not linked it to time yet. Now, I've said it's increasing in the sense that for every time, each instance there is a process, the disorder will increase. And now you see the connection to time, which is where the confusion comes, because you go, that's the origin of that arrow. That's how we can always see there's a direction to it, because the processes are ordered in time, one after another, and every time there's a process, entropy increases, therefore entropy increases in time. Okay. So it's not that time itself will lead to an increase in entropy, it's that any process will lead to an increase in entropy, and the processes are ordered in time. Okay. So, I think last night we had a great egg smashing here, and that was meant to demonstrate something about the nature that's very intuitive of why we as human beings see entropy increasing and always have a notion of an arrow of time. I'm not going to do it, but if I did take one of these eggs and just dropped it on the floor, I would not do it, then there'd be no doubt in your head when this is filmed which way time is flowing. Because it's very rare for eggs that are splattered on the floor to zoom upwards and assemble into an egg.
Very rare.
Very rare indeed.
But possible.
Well, okay, good. So in the laws of physics, yes, that would be possible. Yeah, it would be possible. That, if let me give a really simple one. If you consider a snooker table and all the balls are in a triangle, and you do the break in a bang, and you end up with a whole bunch of things. So each one of those collisions of billiard balls follows Newton's laws, and Newton's laws are time reversible. They work both ways in time. If you think of a Newton's cradle, you watch a Newton's cradle, you can't tell which way time's flowing if you run it backwards. You look at two billiard balls colliding, two of them, you will never tell which way time is running if you run the film backwards. But so each interaction on those billiard balls follows the laws of physics, and each interaction you could run time backwards. But because it starts out with a triangle in a very ordered state, I put them there. Then you know which way time is flowing, even though every collision, if you just looked at two of them at a go, you could run backwards. Because this is the thing about disorder and entropy. It's not about what happens at the microscopic subatomic level, something spooky. It's about how complex systems, I said all the air in this room, my child's room, it required you to have lots of stuff that you're going to order or not. So yes, it is possible to find a perfect shot in billiards that would take all of the balls randomly scattered around a snooker table so that when you hit it, it would just form a triangle. The likelihood of being able to do that shot would be very small indeed. But yes, the laws of physics would allow it. But it would seem so out of kilter with our experience. Yes?
So this may not be the right point to ask this question, but how does that work with an expanding followed by a contracting universe?
Okay.
Singularity expansion.
All right. People are reading ahead. How long have we got? Ask that in 5 minutes, because I need to say a few more things, and then we'll get back to that. So that's Penrose's thing, which I think Caroline's mentioned. So, okay, we'll come back to that. So, we've got this idea of a direction of time and be given by disorder, the growth of disorder. And now you've got to say, well, how can we ever be alive? Because we are not very disordered. No matter how much we think we are very ordered beings. The very notion of life is as an ordered entity that can think, that can do all of the things that are involved in being a conscious being. And this comes back to this notion of having free energy. Have we got anywhere? thus far. Not so sure. So we've got the fact that time is like space, we can talk about it together. We've got the fact that space-time can bend and stretch, can even go in loops potentially, and then create crazy things like going back in time. We've got the fact the origin of the arrow of time seems to be based in thermodynamics, in that processes go, when they occur, lead to an increase in entropy. And now I've told you all of this, I've got to turn it around and ask you a question. Does it help you as a human being, or even as a heat engine with free energy, able to minimize entropy, understand your perception of time? I suspect it may not. There you go. And so now we're left with this other philosophical problem, which is we are humans in the universe that obey physical laws. Nobody suspects that human beings don't obey physical laws. But does all of the ways in which we've explored time and its arrow and its nature help us understand what it is to be human in the way that we perceive time? Some people like it, some people don't. And then, yeah, I can't offer you more than that. That's where we're up to. So, Newton, of course, predates Einstein and described the theory of gravity, Newtonian gravity, and described the motion of planets and so on. Then Einstein came along. We don't actually say that Newton is wrong, because what Newton did was describe things and they were tested, and it was all done within a certain level of approximation, accuracy. So even if in the future, and I suspect we will find corrections to relativity, it's one of the things I work on is actually corrections to relativity. It doesn't mean that Einstein was wrong. It means there'll be regions of the universe where relativity won't work, and you'll need something more. Yeah. But in the regions where we have tested it, we know it's true because it's been tested. Just as in Newton, yeah, it works great. I mean, when I drop stuff, I'm going to drop my watch, when I drop something, this follows Newton's laws pretty well, very well indeed. I'd be a fool to start using general relativity to look at the falling keys. Equally, Einstein's equations work very well in most circumstances, but I can think of a circumstance where they break down, in the core of a black hole, for example, and then we need something more. All I can do as a physicist is tell you the things that we can measure, the theories that we have. Now that you can, that's not about liking, that is just is, right? But what I said to you was, does this help you as a human understand time? Your experience of it. And I said, and that's the bit you can choose to like or not. General relativity says that time is non-linear. So the Western scientific notion of time is as a non-linear entity. But what's not happened is general relativity, unfortunately, because people are not going to do physics degrees enough, has not permeated down into popular culture to the level which we'd like it to do. I think perhaps the dominance in the paradigm of a linear time is tied very much to the Industrial Revolution, because the notion that we had clocks everywhere and that we organised, built on time, and had railways, and the origin of having universal time, for example, in the country was built on having a railway time schedule, which was very useful. So I suspect, and this is what I was saying again, the dominant technologies, the thing which often give us our paradigms of how things work, is that science says time is non-linear, no question. The experience that people have in the Western world is highly dominated by its past as an industrial society and how clocks were used.
Is there a difference between something being real and something being true?
Yes. There we go. All right, now I'll do that. So I can give you a mathematical truth. Let's think. Fermat's last theorem, that for a squared plus b squared plus d squared, no, that's not it. A to the n plus b to the n equals c to the n cannot be true if a, b, and c are integers and n is greater than 2. That's a true statement that took hundreds of years to prove. It's in what way is that real? Because it's a statement about all possible equations of that type, for all possible things. There's no particular instance that's mentioned. I would say the word real should be reserved for nature, and truth actually says more than nature. Yeah.
So what is light? Does different things at different times. It seems simple to all.
Oh, light is an amazing thing. Light is an amazing thing.
What is
I was avoiding doing this, but I'll do light. I love light. So I said, I mean, you know, I'm always trying to avoid the maths, and it's hideous giving you sorts, so I can't do any maths, but I'm just going to give you a fact, which is fun. So I said to you that what relativity really is this business of combining space and time events, right? So if you're over there and you've got your torch and you switch it on at a certain space and a certain time, and the light ray comes to me, or an Alpha Centauri, and it arrives there at a certain space and time, okay? So there are 2 points in space and time that are not the same point. You over there, Alpha Centauri over there. And I said to you, what relativity does is give you a way of combining the distances of space and time together to give you an overall distance. This is going to be difficult. The overall distance that any light ray, the path of any 2 points on a light ray, is 0. The overall distance in space-time between any point on a light ray and another point on a light ray is 0. There is no intuitive way you can imagine that. But so, in some sense, light is omnipotent. Omniscient. It sees everything at the same time. It contracts time down to nothing along its path. So everything that happens along the light ray's path happens in one instant. That's why light's amazing. Yeah. That's why it's an incredibly fundamental thing. It's like some sort of basic thing of the universe in how we measure things. Because of that, it's the 0 distance between points in space-time if they're connected by a light ray.
Can you explain that as a single photon?
Yeah, a single photon will experience things like that. You know? A single photon will not experience time. Light doesn't experience time.
It is in 2 places.
Or more than 2. The whole ray, throughout the whole of its existence, has no separation in space-time to itself.
So light years as a measurement.
Oh, that's a silly thing. So a light year is not a distance as seen by the light itself. That's by seen by you, as measured even in a Newtonian frame. It's completely stupid. It's just saying the speed of light, as was measured years ago, is 2.9979 times 10 meters per second. And then you go, oh, it's very far away. How long would it take something like that to get there? It's watched by me. That's
There's
what
nothing
light
to do
year
with
is.
light at all.
It uses the speed of light as measured by me in a laboratory. That's to do with the light year, but it's not what light will experience. That's all. How we experience time and space as separate things depends on our speed. And it's the fact that light goes at the speed of light means it feels that way. The fact that we are tied to this one way of viewing time is because we move so slowly. Now people have gone with computers and created virtual worlds where we move at near the speed of light and see how things change.
Really?
Yeah. And it's really weird.
How can light have speed if it's the same thing as shooting?
Yeah. Good. No, I like that. Good. So what we do is when we describe the speed of light, that's good. It's not from the point of view of light itself. It's from my point of view, where I have a fixed notion of time and a fixed notion of space. Somebody fires off a light beam, bounce it backwards and forwards things, and then you look at the distance. It's just distance over time.
But that sounds as though...
From my point of view. And that would change if you change your... Well... switching. That was so stupid. So that's what we mean by a light speed, as measured by me. Shining a light, it bouncing backwards and forwards, crossing mirrors, or sent around the world, whatever it is, and then saying how long does it take it, that'll give me a light speed. But that's not what the light experience is itself, that's me in my frame with a view of space and time of what's happened between those two distances.
So what does light itself experience?
It would have no time evolution itself. Go back to the Greeks. The Greeks had the idea of fundamental building blocks of the universe, which they called atoms, and these were thought of as indivisible point-like objects. That notion and idea of the point, the contracted sphere down to the infinitesimal, got carried through for thousands of years, so that when people made atoms and looked at and had experiments and looked at what they thought of as atomic or subatomic particles, the building blocks of nature, they always took this Greek idea of a point-like infinitesimal thing. Okay? So when you've seen pictures in your school books of atoms, they are point-like dots, of red dots and yellow dots and stuff like that, whizzing around in these pictures. What you do as a theoretical physicist is you challenge assumptions that have always been made and never challenged before. So what string theory did was challenge that basic idea that the building block was this point-like infinitesimal thing. And instead said, what if the basic building block of nature was not point-like, was not infinitesimally small, but had extension, like a piece of string, like a loop of string. So then, you look at the consequences of that using lots of maths. That's string theory. We've got a lot here going on. Yes, why don't we have a question from you? Sorry.
My question is this. It's about the concept of who we are in this room. We are like every flower and every movement of the wind or movement of water, every particle of sand, a creature. And we are asking, well, we are trying to create theories, not works of art, not drawings, not paintings, not sculptures. We are creating theories which make us feel, especially with this age of computerization of everything, so we can speed up everything and give us a sense of feeling that we are in command. Because, you know, our God is not art, our God is science. And I'm thinking, is it possible for a human being who is simply like a particle of sand, a creature, or a planet, a creature created in this thing called the cosmos, is it possible for any human mind, including, let's say, Stephen Hawking, okay, who is considered to be able to know the mind of the creator, that was his lifetime's work. Is it the case that we have to have recourse to the language of art rather than the language of science? Because in the end, at the end of his life, even Einstein had to say that what he'd achieved was nothing very much, and that it would soon be inevitably replaced. I'm thinking that it's a question of human weakness and human pride in imagining that we can, as a creature, I mean, I've been 90 years breathing air and living on this planet and seeing whole generations of human beings disappear, okay, into the mystery of whatever death is. And I'm thinking it's very important. For the first time in my life, I find a group of people who are basically using the language of art, considering the language which is considered to be the alternative. You can either spend your whole life developing a theory, or you can spend your whole life making something completely and utterly without rational thought. Because all art is irrational. all art comes from a mystery. Okay, to try to imagine the Mona Lisa or the Last Supper or any drawing by Leonardo, who was a man asking many questions, and think his greatest achievements somehow cannot be explained by any rational thought. But when you look at the Mona Lisa, which I endeavour to do, you just are you're filled with the mystery of, how can I say, the limitations of being a human. If you can live for 90 years, as I have, and still know in the profoundest depths of my being, using rational thoughts, that I know nothing. That all the experiences I've ever had working with some of the greatest minds, that I've come to, that there's no theory, there's absolutely no theory, scientific theory, that comforts me. And here is, of course, the big question. Are we searching for a moment of comfort? Or, we seem to be reliant on people called politicians to comfort us, that they can give us the next 5 years of resolution. And I think one of the things that's worrying me is this separation of art and science. I think this gathering, brought together by Caroline, is very, very important. It's amazing that such an event hasn't yet taken place at the Tate or any of these key places where artists meet. It's, for some reason, identified with a place which is all about the sound of music. And
Richard, can we allow David to answer your question?
Yeah, can you answer that question?
Or they're tempted.
I mean, is it?
No, I can't. But let me make two comments. I think. Let me make two comments. One of them is about the nature of science. You pointed out about how little we can know in any lifetime. You also pointed out the arrogance of human beings to imagine that we can understand the universe in any way. And these are very good points. And this is actually then something of a mystery to nearly every physicist I know as to how successful science has been. In the sense that when it could have been that there was no theory we ever wrote down that corresponded to any experiment ever. It could have been that there was no story for me to tell. But there's been this amazing success. I have no clue why nature has organised itself in, to be honest, such a simple way.
Yeah.
Because I agree with you, we're not particularly clever.
Oh.
Well, I'm not. You.
No, I'm not.
But and even Stephen in his, he says things to sell books. He also knows that, human beings, we live for such a short time.
Yeah.
90 years is, although quite long from our perspective, is nothing compared to the age of the universe, 14 billion years, or the age of the sun. So the fact that we could get anywhere is something of a miracle in its own right.
It is.
And I think it's important to acknowledge that one of the things that you learn as a scientist is actually in some sense how simple the universe is, and that simplicity has allowed us to explain it to some level. But that's about the nature of science. Coming back to my comment before, when I asked you the question, the audience, do you feel happier with what I've told you about time and your experience in it? And I said, I have no comment on that as a scientist. I can only tell you what science says. Whether it finds comfort or explanation into your experience of life, which is your point, is something I can offer nothing for. And then this role of the arts, of religion, of spirituality and all of the things is the fact that there is more to to life than science, though it may be the reason why we do science, at least for some of us, is because we seek those things of beauty, and we do take comfort from the universe having the form that it has. And some of the most beautiful moments in my life have come from understanding theorems, no matter how simple. And I am completely with you that there's been too much pigeonholing for too long. The artist, the scientist, in the end we're all human. And it's something, we've read all for a long time, we've had a whole discussion about what it means to be an artist or not. In the end, we wander around on this little planet and should do stuff.
There's a million questions and we've gone past our allotted time. Do you have some concluding remarks or?
I'll end with that.
Yeah.